So this is the new module that we will be starting of engineering mechanics, and in this new module the first topic that we'll be learning is called as free body diagram. Now free body diagram is basically it's based on forces and the reactions that come on a particular body. For example, you see this is a platform on which a sphere or a ball is resting. Okay. Now what are the different types of forces and different types of reaction that could be acting on the ball? First we'll learn about the forces. So there are two types of forces basically. First is applied forces, that is external forces, any external force which is coming on this ball. For example, you can see this force which is being applied on this ball. It can be from any direction. This is just a representation, a visual representation that I'm showing that a force can be applied on a ball. Then there are non-applied forces. It means inherent forces, or those forces which are already present in all the objects. Due to gravity we have weight, so there is a self weight which is already present, right? So these can be grouped into the term of forces. Next we have reactions. Now this ball or this sphere is sitting on this platform. So the reason that it is able to sit on the platform is because the platform is giving this ball a reaction. So where and how the reactions are given? So these are the two reactions that the platform is giving to that ball, and the reaction will always be normal to that platform or to the surface on which the object is there. Okay, so the reaction would be given normal to those surface where or on which we are placing a certain object. Alright, and when we show all these forces and all the reactions on a particular body, that is called a free body diagram. So what I did here, the ball that was there on this platform, I drew a free body diagram of that ball. Similarly, I can draw free body diagram of this platform also if I want. Okay, so the free body diagram of platform would be that we just isolate that particular term or that particular object separately, and we show all the forces that are acting on that particular object. So here in sphere we have these reactions and different types of forces. On platform, if I try to draw the free body diagram, there will be only two, that is the reaction, these two reactions. Now see, the platform is giving reaction to the sphere. Similarly, I can say that equal amount of force is being put by the sphere on the platform. So this is basically the force that is being put by the sphere on the platform, and both has to be equal because every action has equal and opposite reaction. So this is the reaction, this is the action. Okay, so in simple terms, to say that when we isolate certain objects separately and we try to show all the forces and all the reactions on that particular object, we call that thing as free body diagram. So diagram of the body in which the body is freed from all contact surfaces and is shown with all forces on it is called free body diagram. This is the definition of FBD. Okay, henceforth we will be calling it as FBD, that is the short form. Now there are certain typical cases where we will see how the free body diagram of these cases is shown. First is to draw FBD of this ball which is resting on just a surface. So what are the different types of forces? First we should think that what are the different forces that are acting. Now here let us say that no external force is acting on this, so applied force is not there. Second, we have the non-applied forces or the inherent forces, which is the weight. So weight is there, and then the reaction is there from this surface. So if I want to draw FBD of this ball, this is the FBD, simple. Let us say that now again I want to draw FBD of this ball, but what is happening here is that we have this string that is attached. You can see the string here. Okay, this ball is attached by the string on this wall, and I want to draw the free body diagram of this ball, and plus this ball is also resting on this surface here. Okay, so the reason that it is resting on this surface is because this surface is able to give reaction. Okay, so first let us see what are the different forces that are acting. Let us say that there are no applied forces, there is only non-applied force, that is weight. Due to the weight, let us see what are different things, different reactions. So there is one reaction due to the vertical surface, which is not allowing this ball to go past this surface. If this reaction was not there, this ball would have directly gone in this direction, right? Because this surface is able to give it a reaction, this ball is this ball is holding in that position. Second, what is there is this string is there, that is also holding the ball. So in string we have tension forces. So this tensile or tension type of force is developed in the string. Tension type of force we can understand like, for example, if someone is playing tug of war, one team is pulling from this side, another team is pulling from this side, the rope which is there, it has tensile forces in it. Okay, so when the rope is being pulled from both the sides, that would be called as a tensile force. So this ball is trying to pull the rope. Okay, so a tension is set up inside it. The FBD is this simple thing. The FBD of the ball will be all the forces that are acting on this ball as well as the reactions. Now FBD of a ladder and FBD of this 600 and 400 Newton block. Let us see first of the ladder. What are the different forces that are acting? So here we have two applied forces being acting on this ladder. First is this 100 Newton applied force. Second is this 50 Newton applied force. And non-applied force, again it remains the same, that is the weight of the ladder. Now in every object, this non-applied force has to be applied until that weight of that object is specified. If it is not specified, then we can ignore it, or we can say it is a massless object. It's just an assumption that in some numericals they take that it is a massless object, although it's not very much frequent in engineering mechanics problems, but in other problems, in other subjects, sometimes such assumption is done, like massless pulley or something, like that we do consider. But in this case, we if the weight is given, then we do have to consider that weight. So this is the non-applied force. Then we have the reactions. Now what would be the different types of reactions? One reaction would be given due to this this surface, and one reaction would be given by this surface, right? The FBD would be, this would be the FBD, all the reactions as well as all the forces. Then we have a free body diagram for 600 Newton and 400 Newton block. See, now the two blocks here, 600 and 400. 600 is resting on the surface, 400 is not resting on the surface. The moment something comes in contact with another surface, it means definitely it is getting reaction from that surface. So the moment that this 600 Newton comes in contact with this surface, we can safely assume that the surface is giving reaction to 600 Newtons, right? So for 600 Newtons, we have the weight first of all, then we have the reaction from the below surface, and then we have this tension also, because this 600 Newton is creating a tension in this string. Okay, so there is this tension force also. Then for 400 Newtons is first of all weight is there, and then it won't have a reaction from below because it is not resting on any surface. The next force would be the tension force that it is creating. So this is a tension force due to the string, in the string, due to 400 Newton. Now let us draw FBD for all these four balls. So there are four balls here, and we will draw FBD of each ball separately, starting with the first ball 1. First is weight would be there, weight of that ball would be there. Okay, so let me first draw its weight. I'll say W1. Second, now this ball is resting on second ball and third ball. The moment it comes in contact with the other two surfaces, as I told you, they are going to give reaction to that surface, and the reason that this ball can this ball is resting on second and third ball is because second and third ball are giving reaction to first ball. So these are the two reactions, R2 and R3. Then coming to the FBD of second ball, we have, see now this first ball is resting on second ball. If second ball is giving it a reaction, it means first ball is also putting force on it. First ball will definitely put some force on the second ball. So there is F1. F1 is the force due to first ball on the second ball. Then we also have the weight of the second ball acting downward, vertically downwards. Then we have the reaction. Now this second ball is having contact with this surface and this fourth ball, right? So the second ball is getting reaction from two points. First is due to this fourth ball and due to the surface. So R and R4. R4 is the reaction from the fourth ball and R is the reaction from the surface. Then we come to the third ball. Now this first ball is putting a force on third ball also. So that force would be there. Then its weight W3 will be there, right? Then again the reactions are, it is getting a reaction from fourth ball as well as it is getting a reaction from the surface. So there is a reaction from the surface and then there is a reaction due to fourth ball. And then the fourth one. Now second ball and third ball are putting or applying force on this fourth ball. So we have two forces due to second ball and third ball. We have its own weight W4 and we have two reaction points because these are the 2 points on which that fourth ball is resting. So R and R, I mean they could be of different values. I'll say R dash and R double dash, we can say. So these are the two reactions that it is getting from the surface. So this is the FBD of all 4 balls separately. Next we come to this topic of conditions of equilibrium. Now this equilibrium we have discussed previously also. What is a equilibrium? Equilibrium means that the body is in stable condition and it is not moving, it does not have translational motion, neither it has rotational motion. So the meaning of this is that if there cannot be a force which causes a horizontal movement, if there is a force which is causing a horizontal movement, it means definitely that body is not under equilibrium. So there cannot be a force which is causing a horizontal movement, therefore no net horizontal force, or we can say summation f of x equals to 0, that is summation of forces in the x direction all have to be 0. Okay, this is first condition of equilibrium. Second, if there is no horizontal movement, there cannot be a vertical movement also. If there is a vertical movement, it means that it is not under equilibrium. So no vertical movement also, right? So no net vertical force. Summation Fy equals to 0. This is another condition of equilibrium. Then we have, if the body is rotating, again it cannot be under equilibrium, because if an object keeps on rotating, obviously it is getting displaced from its original position, so it cannot be under equilibrium. Therefore no net moment or no rotational effect. So we can say that summation of moment is equal to 0. So summation of moment on any point on this body has to be 0, because if any point is experiencing a rotational effect, it means that it is causing disbalance to this object. Therefore, any point on the object has to have no rotational effect, or summation of moment on that point has to be 0. So these are the three important, very important conditions of equilibrium. Summation fx equals to 0, summation fy equals to 0, and summation m equals to 0. Next, after knowing these three conditions of equilibrium, now let us come to the two separate types of forces that force systems that we have learned. First is concurrent force system, which we know that their line of action, it meets at a single point, or the forces, they originate from a single point, that is there. And second is non-concurrent force system, which we'll be learning much later on, but first we will deal with concurrent forces. So when I am talking about equilibrium of concurrent forces under equilibrium are satisfied by only two conditions of equilibrium. We have learned three conditions of equilibrium: summation fx equals to 0, summation fy equals to 0, and summation m equals to 0. But concurrent forces are satisfied by only two conditions. Which are those? Summation fx equals to 0 and summation fy equals to 0. Okay. When I say that concurrent forces are under equilibrium, it automatically means that there is no moment at any point, or summation of moment of concurrent forces under equilibrium is already 0. Okay, so still there are three conditions here, but when we say that there is a system, a concurrent force system, and if I tell you that this concurrent force system is under equilibrium, it automatically means that summation of moment of those forces at any point is going to be 0. Now how and why, we'll see. Let us consider this simple example of concurrent forces which are under equilibrium. See, this is a very simple example I have taken. All the forces, they cancel out each other, so we can say that their net horizontal effect is 0, their net vertical effect is 0. Yes, their net horizontal and net vertical effect is 0. So I can call these forces concurrent forces under equilibrium. Now let us prove that the summation of moment at any point is 0. So first, why not take this point O only, because we already have that point with us, right? So let us try to find the moment at point O. We can directly say that the moment at point O due to all the forces is 0, as point O is on the line of action of all the forces. Because this point O is on the line of action of all these forces, directly we can say that there cannot be any moment due to point O. Due to all these forces on point O. Fine, this is easy. This was easy. Why not take some other point? So let us take any other point and try to find moment about that point. So let us say that this point A is at a distance of x and y. Okay, so the coordinates of this point A is x, y, and I will try to take moment due to all these forces about point A. So summation of moment at A, and due to this first force, let us say, so this first force, if I try to resolve it, F cos 45, F sin 45, F cos 45 multiplied by Y is going to give me an anti-clockwise moment about A. Understand this very carefully. F cos 45 multiplied by the perpendicular distance is Y is going to give anti-clockwise moment about A, so that is plus F cos 45 into Y. Then F sin 45 multiplied by X is the perpendicular distance. See, this resolving of the force, I have shown it at this point, but it's actually at this point, right? Just to avoid the confusion, because it's not seen properly, that's why I did not draw it. But this is your F cos 45 and this is your F sin 45. Anyways, I'll just draw them. So f sine 45 multiplied by x is going to give me a clockwise moment. Therefore, it is minus f sine 45 into x. Now, coming to the second force, this is your f cos 45 and this would be f sine 45. So f cos 45 multiplied by its perpendicular distance is going to cause a clockwise moment. Therefore, it is minus f cos 45 into y, and f sine 45 multiplied by its perpendicular distance x is again going to cause a clockwise moment. See, like this, about point A. So it's a negative moment again. Fine. Let us talk about this third force, which has its horizontal component this way and vertical component like this. So this is f cos 45, this is f sine 45. F cos 45 multiplied by y is going to cause a clockwise moment, so it is minus f cos 45 into y, and f sine 45 multiplied by x is going to cause an anti-clockwise moment about point A, so it's plus f sine 45 into x. Coming on to this last force F, we have f cos 45 in the right direction and f sine 45 vertically downward. So f cos 45 multiplied by y is causing an anti-clockwise moment, so it's positive. And we have f sine 45 multiplied by x again causing an anti-clockwise moment, so it's positive. Okay. Now you see, this f cos 45 into y, this gets cancelled, then this and this gets cancelled, then this and this gets cancelled, everything gets cancelled, and we get summation of moment at A as equal to 0. So as I already told you that of any concurrent force system which is under equilibrium, the summation of moment at any other point is already equal to 0. So we are not it's not like we are not adhering to our three conditions of equilibrium. We are actually adhering to our three conditions of equilibrium, that is summation fy fx equals to 0. Apart from that, summation m is already equal to 0, right? So all the three conditions are being met. So similarly, it can be proven that moment at any point for a concurrent forces under equilibrium is 0. Equilibrium of concurrent forces. Again, now if, listen to this statement very carefully, if only three forces are under equilibrium, they have to be concurrent. If only three forces are under equilibrium, they have to be concurrent. Why? Why is this so? Let us see. Let F1, F2 and F3 be three forces under equilibrium. So it means that summation Fx, summation Fy and summation m equals to 0, right? All are three conditions, and summation m equals to 0. All are three conditions have to be met for a particular system to be under equilibrium, right? So if these three forces are under equilibrium, these are met. Fine. Let line of action of F1 and F2 meet at point A. So I can say that these two forces are at least concurrent. This is what at least I can say. Now since I have extended the line of action and I made them to meet at point A, I can say that this F1 and F2 are at least concurrent at point A. But F3 is not concurrent, if you see. So according to condition of equilibrium, the summation of moment at any point on the body has to be 0. So since I am already telling you that these three forces are under equilibrium, it means that this condition is true. It means that any point on this body is going to have summation of moment as equal to 0. Same is true for point A also. So let us take summation of MA equals to 0. Summation of moment at A equals to 0. Now obviously due to F1 and F2 there cannot be any moment at point A because point A lies on their line of action. This we know. The only doubt is of F3. So F3, let D be the perpendicular distance from line of action of F3 till point A. So F3 into D has to be equal to 0, correct? Because we need summation of moment at A equals to 0. But F3 cannot be 0 because it is a magnitude. There is a force, right? And we cannot say that this force is 0. We already know it is there. So what should be 0? This distance has to be 0 then. If F3 is not 0, then obviously the distance has to be 0. So we can say that F3 is also concurrent at this point A, and thus we can say that if only 3 forces are there which are under equilibrium, they definitely have to be concurrent. Alright. Now we have this Lamis theorem. Lamis theorem states that if a body is in equilibrium under action of only 3 forces, so again here the 3 forces only come. So if it is under equilibrium, these 3 are already under equilibrium, they are also concurrent, then what we can say is that each force is proportional to the sine of the angle between the other 2 forces. So what it is saying is that these 3 forces are under equilibrium, so each force is proportional to the sine of the angle between the other 2 forces. It means that F1 divided by sine of angle between other 2 forces, means angle between these 2 forces is alpha. This is equal to F2 upon sine beta, which is the angle between the other 2 forces, is equal to F3 upon sine gamma. So this is your Lamis theorem. And let us prove it. Okay, we won't take anything without proof. So let us prove this. Let's say this is F1. I form a triangle by these 3 forces. Okay, and let us say that this is F2. Alright, what I have done is actually just expanded them. Like F1 is parallel to this side of triangle is parallel to F1. This side of triangle is parallel to F3 and this side of triangle is parallel to F2. So between F1 and F3, like this is F1, this is F3, we have this angle as beta. Then between F2 and F3, that is F2 and F3, we have this angle as alpha, and between F1 and F2 we have this angle as gamma. Correct? And also let us name them A, B and C. So this angle should be 180 minus alpha, this angle should be 180 minus beta, and this angle should be 180 minus gamma. We can apply sine rule here. So AB upon sine of 180 minus alpha, that is this sine opposite to it, is equal to angle opposite to it is equal to BC upon sine of 180 minus beta, again the angle opposite to beta, and is equal to AC upon sine 180 minus gamma. So this is how we apply sine rule. Now we understand that sine of 180 minus theta is sine theta itself. Okay, so we can say that this is, and AB is your F1, BC is F2, AC is F3. So we can say F1 upon sine alpha is equal to F2 upon sine beta is equal to F3 upon sine gamma. Hence proved. This is our Lamis theorem. And we should note that Lamis theorem is only applicable for 3 forces. You cannot apply Lamis theorem for more than 3 forces. Very, very important note. You cannot apply it for more than 3 forces, and those 3 forces necessarily they have to be under equilibrium. Only then you can apply Lamis theorem. Otherwise you cannot apply Lamis theorem, and obviously if the three forces are under equilibrium, they will definitely would be concurrent as well. We just saw previously, right, that they should also be concurrent. So that's it for this lecture. Till then, take care. Thank you.